Hello everybody, welcome to Chapter 4.1 Part 2, Properties of Mathematical Systems, More Examples. In example number 4, we're going to identify properties and consider the following table. So the system shows elements with 0, 1, 2, 3, 4, and 5, and the operation is x with a circle around it. Which properties are satisfied by this system? Let's see that if in the body of this table, meaning in here, there are other elements besides 1, 2, 3, 4, and 5. Well, we can look. We see zeros, we see 1, 2, 3, 4. We can examine it, and we notice that there are no other elements besides 0, 1, 2, 3, 4, or 5. So therefore, closure is satisfied. Now, let's draw a diagonal through the table and see if what's on this side of the diagonal is the mirror image of what is on this side of the table. So let's see, we have 0, 0, 0 here, 0, 2, 2, 3. If we fold along the diagonal, the zeros will correspond to the 0 here, the 3 will correspond to the 3 here, the 0 will correspond to this 0 here, etc. So that means that there is symmetry, and this means that commutativity holds for this particular system. So the system satisfies closure. All the numbers in the body of the table come from the set 0, 1, 2, 3, 4, 5. So the system is closed. Commutativity, when we draw the diagonal, we get symmetry. Associativity, well, this one we actually have to check with some examples. So let's try a few examples. I'll choose 2, cross, circle, 3, cross, circle, 5. And I'll put the brackets here for this one, and I will work this one out using our order of operations. So here we do our brackets first. So I go to 3, and then 5 here, and 3. So I end up with 3 here. So that means I take the 2 from here, take the cross circle, so 2 cross circle, and the 3 I just found from 3 cross circle 5. And now I do 2 cross circle 3, and I get 0. Let's put the brackets here in the front. So I do 2 cross circle 3. So I have 2 cross circle 3, and I get 0, and then I do 0 cross circle 5. And here I go 0 cross circle 5, and I get 0. So in this case, associativity holds. Why don't you try a few more examples to see if it holds in other situations? Now let's see if the identity property holds. So the identity element in the second row is repeated and the second column. This implies 1 is the identity element. So here, as we see, 0, 1, 2, 3, 4, 5, 0, 1, 2, 3, 4, 5, and here's 1 up here. Let's try it for the rows. And indeed, it's true. 0, 1, 2, 3, 4, 5, and here is the 1. So it appears as though 1 is the identity element. The identity element is implied because the column at the left of the operation table is repeated under 1 in the body of the table. 1 is the candidate for the identity element in this system. To be sure that 1 is the identity element here, check that the row corresponds to 1 at the left-hand side and is identical with the row at the top of the table. Since it is, this implies 1 is indeed the identity element. To find the inverse elements, we look for the identity element 1 in the rows and the columns of the table. So 1 cross circle 1 is equal to 1 at the bottom row, and 5 cross circle 5 is equal to 1. So 1 and 5 are their own inverses. There is no identity element in the rows columns opposite the numbers 0, 2, 3, and 4, so none of these elements has an inverse. In example number 5, we're going to identify properties of the Garfield operation. So we're going to decide which properties are satisfied. So let us look at the top here and the side here, and we see there's math, math. Now let's look inside the body of the table, and are there any other letters besides M, A, T, and H? And we see there are none. That means closure is satisfied. Now let's draw a diagonal and see that if we fold along this diagonal line, will the M's match up, the A's match up, the T's, the H's, the M's, etc. And indeed, it looks like they do match up. So that would mean commutativity holds. So the Garfield system satisfies closure. This implies that all the letters are in the body of the table come from the original set M, A, T, H, so the system is closed. Commutativity implies that if we draw a line from the upper left to the lower right, we can fold the table along this line and have corresponding elements match. The system has the commutative property. For associativity, we have to try some examples to see if associativity holds, at least in those examples. So for our first example, we're going to take MAT, and we're going to put the brackets around the AT. So we find that when we look at the table, AT, because we have to use our order of operation rules, we have A, T, and they cross at T. So then we're left with M, Garfield, T. Now we look at M, T, and they cross at A, so we end up getting A as our final answer. Now we're going to put the brackets around the M, Garfield, A, and we're going to do that one first. So let's look at M, A, and they cross at M. So now we have M, Garfield, T. Now let's look at M, T, and then they intersect or cross at A. So it appears for this particular example, in both cases, no matter where we put the brackets, we will still get A. So M Garfield bracket A Garfield T bracket is equal to M Garfield A bracket Garfield T. Now let us try another example. We have H, Garfield, T. And we first put the bracket around the second HT. And we see when we do that, because we have to do the one in the bracket first based in order of operation. So let's go to H, T, and they intersect at M. So that means we're left with H, Garfield, M. Now let's go to H, M, and they intersect at T. Now let's put the bracket around the H, Garfield, H, and that means we'll look at that one first. So let's go to H, and they intersect at A. So we're left with A, Garfield, T. Now let's look at A, T, and they intersect at T. So here again, it doesn't matter where we put the bracket, even though we have the H repeated twice, we still end up getting T as our final answer. So H Garfield bracket H Garfield T bracket is equal to bracket H Garfield H bracket Garfield T. So why don't you try a few more? Now let's look at the identity property for Garfield. And we want to look at where math, M-A-T-H, exactly where it shows up, is repeated. And here it is under the A. And then we want to see where it's repeated in the row. And again, it's next to the A. So that means A is the identity element. So the identity property implies because math is repeated to the right and below the A is the identity element. For the inverse property, yes, M Garfield T is equal to T Garfield M, which is equal to A. A Garfield A is equal to A, and H Garfield H is equal to A. Thus, every element of Garfield has an inverse. For example number 6, we're going to look at the donut operation and decide which properties are satisfied. So the first thing we're going to look at is closure. And we see that the set consists of 1, 2, 3, and 4. And this is also 1, 2, 3, and 4. So we look in the body of the table and see if there's anything other than 1, 2, 3, or 4. And we see there isn't, so we can conclude closure is satisfied. Now we'll draw the diagonal down the table and fold it to see if there is a symmetry. And indeed there is. The 3 corresponds to the 3, the 2 corresponds to the 2, the 4 corresponds to the 4, etc. if we fold it, and that means the commutative property holds here. So closure implies all the letters in the body of the table come from the set 1, 2, 3, 4. So the system is closed. Commutative implies if we draw a line from the upper left to the lower right, we can fold the table along this line and have the corresponding elements match. For associativity, we have to check the associative property by trying a few examples. So let's do 4 donut 3 donut 2, and we'll put the brackets around the 3 donut 2. So we look at our table here, the donut operation, and we see 3, 2 intersects at 4. So we have 4 donut 4. Now we look at 4, 4, and it intersects at 4. Now we're going to do 4 donut 3 donut 2, but this time we're going to put the bracket around the 4 donut 3. So let's do the 4 donut 3 first. So 4, 3 intersects at 3. So then we're left with 3 donut 2. So we go to 3, 2, and that intersects at 4. So we see wherever we put the bracket, it doesn't matter, we will still get 4 as our answer. So 4 donut 3 bracket 3 donut 2 is equal to 4 donut 3 bracket donut 2. Now let's try another one. 3 donut 2 donut 1, and we'll put the bracket around the 2 donut 1. So that means we'll do the 2 donut 1 first. So we go to the 2, 1, and we get 3. So that means we get 3 donut 3. And we find when we look at 3, 3, we get 1. So 3 donut 3 is equal to 1. Now let's put the bracket around the 3 donut 2. So we do the 3, 2, and we get 4. So now we have 4 donut 1. So now we look at 4, 1, and it intersects at 1. So here again, it didn't matter where we put the bracket, we still got 1 as our answer. So 3 donut bracket 2 donut 1 close bracket is equal to 3 donut 2 close bracket donut 1 is equal to 1. It looks like associativity holds in these cases. Why don't you try a few more? The last definition we're going to discuss in this chapter is the distributive property. For example, let heart and degree be two operations defined for elements in the same set. Then heart is distributed over degree if we have a heart and we multiply that into B degree C, and we end up with A heart B degree A heart C for every choice of elements A, B, and C from this set. Thank you very much. I hope that you liked this video. Be well, take care, and goodbye for now.